In this video we're going to look at continuous random variables. And continuous random variables are random variables that can assume an infinite number of possible values between two values. For example, if you're measuring the actual height of a child whose height is somewhere between 140 and 145 centimetres tall, in theory that child could be, depending on the tool that you use to measure them, 141.37245 with all these other decimal places after it, an infinite number of decimal places. So we have an infinite number of possible values here. So to record continuous random variables, we'll use frequency tables. So here's some data that I've put together in a frequency table just to remind you how it's done. So we've got 20 pieces of data here, and I've organised them into categories where they fall between and in, starting from 0 up to, but not including 1. And that is 6 numbers fall into that category. 1, 2, 3, 4, 5, 6. There they are. The numbers that fit from and including 1 up to but not including 2 are these numbers. And finally, the numbers that fit equal to or greater than, equal to or greater than 2. So x is between 2 and just under 3. And they are these numbers here, including the 2.999 with infinitely recurring 9s, because that is not 3. So we organise our continuous random variables into frequency tables. And then if we wanted to graph them, we graph using the data from the frequency table into histograms, displaying the classes, the class widths along the horizontal line. So our first class, our first group, goes from 0 to 1. So it starts at 0 and it finishes at 1, and this area here shows that represents the values. It represents our 6 values. I'll show you the 6 here. And then the values from 1 to 2, between 1 and 2, they're all contained in there, and there's 6 of them. So we put it up to 6, and that contains the 6 of them. So we're going to display those using histograms. Now that's fine for small amounts of data, but if you have really large amounts of data, you don't want your frequency axis going up to thousands and tens of thousands. What would be more useful data is to have those particular values as relative frequencies. So this is talking about turning our data values, our frequencies, into percentages. And so you can see that's what I've done here. And so I've got, for 0 to 1, our frequency of 6 was 6 out of 20 data points, which is 30%. That makes more sense, a bit more information about the data than just the number 6. And so you can see I've changed all of my frequencies into a relative frequency, and now I've got relative frequency or percentages as my vertical axis. My data still looks the same. If I wanted more information about the data, I could break the categories down into much narrower categories. So you can see here I've split my 0 to 1 category in half, and now I've got 0 to 0.5, and there's 4 data points that were in that, and 0.5 to 1 there was 2 data points in that. And so you can see I've got 2 separate columns here. This is the 0 to 0.5, and this is the 0.5 to 1 column. Our 2 data points, that our category that made up 6 or 30% has now been split in half as well, and half of the values went into each, so half and half.
And for our final data category, when we split the x values in half, so from 2 to 2.5 and 2.5 to 3, 5 of the data values were in the first half and 3 were in the second half. And you can see that I'm getting more information about how the data is spread. So as the width of the intervals approaches 0, so as I make these intervals narrower and narrower, and I'll have more and more and more categories here, you get a more accurate picture of the data. And in fact, when you get an infinite number of columns that are infinitely thin, you can end up with an overall shape like a curve. And that curve is created by joining the middle of the tops of all of the columns together. And when you do that with tiny, tiny, thin columns, you get a nice, smooth curve that fits the data really well. And this curve is what we call a density curve. And it shows all the data points in the continuum along here. So this is a density curve. So density curves are used to visualize a distribution, and they contain all the possible outcomes along their x-axis and within their curves. So 100% of the outcomes are contained between the endpoints of these functions, these curves, the curve and the x-axis. And they come in all different shapes. So here's some here. There's a density curve, another density curve. This could be a density curve. This could be a density curve. But the area under the curve contains all of the outcomes and their relative frequencies. So a density curve also has a couple of other properties. All of the y values for the curve are positive or 0 because they're relative frequencies. So this is one of the properties of a density curve that you can check out. And the other one is that the total area under a density curve is equal to 1. And we know that the area under the curve you integrate, and all of the x values, all of the possible x values from negative infinity to infinity, if you integrate that, it's equal to 1. So these are the properties of a density curve. So one of the questions you'll get with probability density functions is whether a function is in fact a probability density function. And so the two things you need to check are, is the function itself always greater than or equal to 0? And is the area under the curve equal to 1? So the easiest way to check these things is often to have a look and see what the function looks like. And here's what it looks like. So you can see I've put it in as a hybrid function into my CAS calculator. For the elsewhere bit, I've just left that blank. And you can see that the function itself is 0 for everywhere else other than x is equal to 0 to 1, which is this bit in here. Then it looks like that. Everywhere else it's 0. So there's no area underneath these lines where the function is equal to 0. The only area we have is between x equals 0 and x equals 1. So our first condition is the function itself greater than or equal to 0 everywhere. The answer is yes. It sits on the x-axis or above the x-axis anywhere. The other one we would need to do on our calculator, we would need to integrate between 0 or 1, or we could use the bound area function on our CAS calculator, and if we did that, it'll tell us that the area is 1. So this is a probability density function. So we can use density curves to find probability. So we know that we use the area under a curve to find particular probabilities. So let's talk first of all about the idea of finding the probability that x is some particular value a. So here's our value of a for x, and we're trying to find the area under the curve at that point. Now, the point up here on the curve, that point there, I'm going to draw it, is actually infinitely small. It's infinitesimally small. And in fact, it's so small that it has no area underneath it at all. And if we did define it to have the tiniest bit of area, then every single point on here would have a tiny little bit of area, and before you know it, our area would be greater than 1. So by definition, for a density curve, the probability that x is equal to a particular value is equal to 0. So this is a definition. This is something that you need to remember. It throws kids. Okay, so the best that we can do is to find probabilities between two values. So we can find the probability that a particular outcome will be between the value of a and b. So we're looking for the probability that x is between a and b. And to do that, you integrate the formula for the density curve between a and b. And yes, I did just use integration in probability. Now our definition from up above makes for some interesting thinking happening with our continuous random variables, which is different to our discrete random variables. Because the probability that x is equal to a particular value, we've got an equal here, is actually 0, what we've got by definition is that those two probabilities are the same, as are these two probabilities, that a is less than x and a is less than or equal to x. For continuous random variables, they are the same, and these ones are the same. So let's do a quick comparison between our discrete random variables, which are these ones here, and our continuous random variables, which are these ones here. So in our discrete case, we have a probability function, which is p of x. In our continuous case, we have a probability density function, which we define to be f of x. In our discrete case, all of our probabilities are greater than or equal to 0, so they have positive values. For our continuous case, it's our function, which is greater than or equal to 0, and that's so that we get a positive area. For our discrete random variables, the sum of all of the probabilities has to be equal to 1, so the total probability is equal to 1. For our continuous case, the area under the curve is equal to 1. So total area is equal to 1. And the biggest difference comes with the finding of the probability between two values or equal to two values. So if we wanted to find the probability that x was between a and b, for a discrete probability function, what we would do is we would locate a and b in the probability table, and we would add all of the probabilities between those together, including a and including b, because less than and equal to means less than and equal to for a discrete random variable. For the continuous random variable, we integrate between a and b, the same kind of deal. But here we have that specific rule that the probability that x is equal to a particular value is equal to 0. So this is the one thing that we need to watch out for here. Watch out for this. That's a main difference. Now let's look at some of our measuring tools. So we'll use our definition for mean, median and mode from our binomial distribution. So our mean is the balancing point of the distribution, the point at which you would place the point on which to balance the whole distribution. So it's a theoretical value, it's an x value here. So the mean is going to be this x value. So the median is the second quantile, or the 50th percentile. So what you're looking for is the area from the lowest value, that should say negative infinity, up until m, that gives the area under the curve equal to a half. You could also come from positive infinity down to m, but that m value will be your median. The mode is the x value for which the function has its maximum value. So for this density curve here, the mode is the x value, so this value here, that sits underneath where the function has its maximum. So this is the function maximum, and that value there is the mode. So in this case, the mode is equal to 0. So don't get tricked into writing the function value maximum. You're actually looking for an x value, that is the mode. So the last thing I want you to do with mean, median and mode is keeping those things, those ideas in place. Have a go at writing mean, median and mode for A, B and C for each of these distributions. And I'll give you a heads up, sometimes one of the letters is more than one of those three things. Press pause, have a go, and then check your answers. How did you go? Mode, always under the highest peak. So A and C are the same height. You might have had one higher than the other. And C as the mode here. The median is your middle point. So for this one in the middle, it's wherever it's symmetric, the point of symmetry here. And if you have a point of symmetry for your two halves, then whatever that x value is will be your median and your mean. Okay, your median and your mean, if it's symmetric, is the middle point. This is symmetric. When you have the skewed graphs, you have to decide B and C, which is the median and which is the mean. And it might be a little bit counterintuitive, but what you actually have, this long tail here and this long tail here, actually drags the balance point back out this way further. So the furthest away from the mode is the mean, so this one is the mean. And for this one, the furthest away from the mode here is the mean, so C is the mean.